Hi there, and whether you're just looking for a quick review or genuinely struggling with this concept, I know this video will be the optimal solution to your problem. But all bad puns aside, let's get started with our look at book section 4.7, Optimization. Before we begin, it's a good idea to look at some of the key concepts behind optimization. Since Chapter 4 is all about maximums and minimums, it should come as no surprise to you that at its heart, optimization is pretty much just finding the absolute maximum or minimum of a certain function. The catch here is that it does so with two different functions, one that you're trying to maximize or minimize, and another that serves as a constraint or a sort of limiting factor to the first function. We'll dive into that later. And both the function being optimized and the constraint will typically have more than one different variable, but never fear. Remember that you've got two different functions, which means that with a bit of work, you can just substitute the constraint into the function being optimized. This kills two birds with one stone. Not only do you get rid of the pesky extra variable, but you're left with just one function that you can get straight to optimizing. So let's talk about how we do that. There's some good news and some bad news about optimization. The bad news is that it's made of word problems, so it's not one size fits all. You can't just take the same formula and plug in the same types of values again and again and again. Well, I mean, if you really like math, maybe that's good news, but either way, the real good news here is that there's a simple 7-step process that you can use to solve any optimization problem, and we'll be working through a couple practice problems with that in mind. Let's start fairly easy with this one. So, the other day I was walking along a river when I met my fine farmer friend, Mr. McDonald. McDonald had 200 yards of fence all piled up in a bit of a dilemma. You see, he wanted to create the largest possible space for a sheep, but he wasn't sure of the dimensions of the rectangle that would yield the largest area. He knew that he could use the river to his advantage and get rid of one of the sides, but it had been a while since he'd been in calculus and he didn't have the energy for guess and check. Like the good old pal I am, I offered to help him out. So let's work the problem, shall we? According to our list of steps, the first thing we need to do is extract useful information. Here, we can see that McDonald has 200 yards of fence. We'd call this the perimeter, but the river happens to block off one side perfectly, so it's really just 3 of the 4 sides. We're also looking for the largest area, which sounds like what? You guessed it, the maximum area of a function. After that, it generally helps to draw a picture. We can illustrate the river on top with this lovely and very realistic blue rectangle and the fence making the other 3 sides. Here's also a good place to introduce some variables, L for the length of the fence and W for its width. Our third step is to determine an equation, or to be more precise, 2, the equation being optimized and the constraint. Looking back at our beautiful picture, we notice that the amount of fencing, 200 yards, is equal to 2 times the width plus the length. We also notice that the standard formula for a rectangle's area equals length times width, still applies. Since we want to maximize area, we're going to find a way to substitute our other equation, the constraint, into the area formula. Actually, it's pretty easy. A bit of basic algebra shows that length equals 200 yards minus 2 times the width. If we stick this into the area formula, we get that the area equals 200 yards minus 2 times the width, all times width again. That leaves you with this very nice looking equation right here. Our fourth step is to find the derivative of that equation. All we need to use here is some basic power rule, and we find that a prime of the width is equal to 200 minus 4 times the width. Seems to work well. After that, we'll find and test our critical numbers, plus our endpoint since we're looking for an absolute maximum here. Set the derivative equal to 0 and you get the single value of width equals 50 yards. If we stick this into the equation 200 yards equals 2 times the width plus length, we see that we're using 100 yards on length. This gives us the dimensions of 100 yards by 50 yards and a maximum area of 5,000 yards. Pretty convenient, but we will be ramping it up a bit later. Here's a good time to also introduce the endpoints to our function, which happen to be width equals 0 and width equals 100 yards. Why? One of these gives the maximum length of 200 yards on one end, and the other uses all the fencing just on width, or 100 plus 100 equals 200. Unfortunately, we can't really plug either of these into the area function without getting out an area of 0, so these can't be our maximums. Our sixth step is to actually answer the problem. Be careful because the maximum or minimum value itself won't always be the answer. In this case, in fact, we're looking for not the maximum area, but the dimensions that produce it, just 100 yards length by 50 yards width. Remember to always include units. A 100 nanometer by 50 nanometer area would be tiny, and a 100 mile by 50 mile one would be gargantuan. And if you've got time, an excellent bonus 7th step is to check your maximum or minimum with the second derivative test. It's power rule again to get the second derivative, which happens to be a double prime is equal to -4. This indicates that the function is concave down at that point, so the maximum really can be on top. Now that we've got the basics, let's ramp it up a little and breeze through another problem. Pause the video, read the problem, and jot down some relevant information before we begin. Great! Here we can probably expedite things by combining the first and second steps. When we draw a picture, we see that this is really just the same as 2x squared minus 12 shifted down 1. So we can redraw the picture just using the x-axis as we were using y equals -1 before. Since the y-axis splits our rectangle in half, we can label it as such, and we can also notice that the x-intercepts of the parabola are at square root 6 and negative square root 6. Interestingly enough, at x on the rectangle, the width, or y, happens to be equal to negative quantity 2x squared minus 12, since we're kind of taking the absolute value here. Same thing goes for negative x. Coming to the third step, we want to maximize the area of this rectangle, which is equal to length times width, or 2xy if we look back at our picture. When we put our new y value into this, or y is equal to negative quantity 2x squared minus 12, we get this equation right here. Now we want to take the derivative of that, giving us a prime of x is equal to negative 12x squared plus 24. Where is this equal to 0? When x is positive or negative root 2. Since the length is really the distance of both the x's together, and you can't have negative distance, you see that length is 2 root 2 units. But that's not all. Plug x into our equation for the y value, and we see that here y is equal to 8 units. This rectangle happens to be 2 root 2 units by 8 units. Alright, third and last problem, you guys. We're almost there. Pause the video and go ahead and jot down some of your relevant information here. Got what you need? If not, that's okay. It seems like the primary goal of Thrixus is to maximize his profit, so we'll have to find the maximum value of the profit function. The cost of each rug is $100, which will be useful for setting up that function. So all the information about the demand, which is, luckily for us, linear. Drawing a picture honestly isn't going to help us much here, so we can just skip right to step 3. We'll need to set up several equations here to get to our preferred profit equation, so let's stick those all on the board, shall we? Remember, P of x is profit, D of x is demand, R of x is revenue, or the amount of money being made, and C of x is cost, or the amount of money being spent to make the items. The easiest thing to start with is finding the cost per item. It's right in the problem as $100 per rug. Now we've got to find the demand for rugs, so how much money people are willing to pay. Since it's linear, we're looking for M and B. It seems like we can find M with the average change in rugs bought with cost. So M is equal to this, or -30. To find B, the baseline demand, we've got to plug in one of the original values, so that yields a B of 2100. The total revenue is the demand times the number of rugs, so R of x is equal to -30 x squared plus 2100x. Now that we've got our revenue and cost functions, we can just stick them in the profit function and end up with this. Well, now that we're done with the hard part, we can pretty much coast from here. Next, use the power rule to take the derivative of the profit function. Set that equal to 0, and you get a maximum x value of x is equal to 100/3 rugs. Now, granted, you can't really sell a third of a rug, but hey, maybe a customer just wants something from a small space. That could work great. We're not done yet, though, because we need the price of the 33 1/3 rugs, and for that, we need the demand function we found earlier. We see that Thrixus should sell his rugs for $1,100 each. We can also check 100/3 with the second derivative test. P double prime of x is -60, and so is P double prime of 100 thirds, so that right there is optimization. Just stick with the process and you can't go wrong. See you around!